All right, thanks. So thanks for the introduction. I'm going to start just by talking a little bit about Georgia Tech and GTRI, and then I'm going to get into how our group is utilizing ROS and why we see so much value in ROS, and go into just a couple of different areas that we've been applying. I think that most people are familiar with Georgia Tech as the school. We do have undergraduate engineering programs ranked anywhere from #1 to #4 in the country. We also have graduate engineering programs that are highly ranked. We're also very proud of the fact that we are #1 in the country in granting minority engineering degrees, as well as #3 in granting women's engineering degrees. We have quite a large academic faculty and research faculty, but the area that I'm going to talk about more today is how GTRI, or the Georgia Tech Research Institute, fits in with that. And at GTRI, we do contribute over 577 million of the 1.9 billion that Georgia Tech does bring in every year. And we have 2,700 employees with 1,500 or so research faculty. And as you can see by this fiscal growth chart, we have been doing very well in the last couple of years and are experiencing very rapid growth. So this is a plug that if any of you have students or yourselves are interested in looking for jobs in the research area, please do consider getting in touch with us. We do have a pretty comprehensive jobs board that is in the public domain area. Just a little bit about our history. The Georgia Institute of Technology, or Georgia Tech, was founded in 1888. And really it was founded to move the South from an agrarian to an industrial economy after the Civil War. Georgia Tech Research Institute was founded in 1934, and it was trying to help jumpstart the Georgia economy after the Great Depression. The original focus was on applied technologies to engineering, manufacturing, agriculture, and industry. And during the Cold War, we really evolved into being more of a national security institute. Although the vision that I'm going to be speaking about today still does quite a bit of work in manufacturing, agriculture, and industry. We actually, for GTRI, have two large locations, one that's in the heart of Atlanta on the main campus of the university, which is where I am located, and this is about 858,000 square feet and 14 buildings. And then we have another larger facility that's about 965,000 square feet that's located about a 20-minute drive north of campus. And in addition to that, we have 22 field offices that are scattered around the country, as you can see in the map here. The group that I'm going to be talking about today is the Intelligent Sustainable Technology Division. And we really try to develop advanced technology and systems that are going to improve the human condition through transforming the agricultural and food systems, sustainable use and access to energy and water, and the safety of people at work and from pandemics. We have 37 research faculty and anywhere from 40 to 80 students. It depends on the time of year. And we have quite a broad research focus with everything from robotics to data analytics and machine learning to energy capture and storage. But in particular today, what I'm going to emphasize are our knowledge-driven robotics portfolio of projects. And really what we're trying to do here is taking dumb robots and making them flexible, agile, and able to detect and correct for errors. And in this, we have lots of different domains that these robotic systems function in, and I'm going to show you just one or two of those domains in the remainder of this talk. But really, we have two items that are in common. We apply a standardized knowledge-driven robotic architecture and framework to all of these systems. And we try to develop reusable components that have application across projects and across domains. Really, the main areas of research that I'm going to focus on for the remainder of this talk are the autonomous architecture and planning systems that we are utilizing. And this includes standard interfaces for tasking and control. It allows us to have concurrent operation of multiple systems, and we're really striving to have this be robot and vendor agnostic. And then the second area that I'll show a little bit about are low-level controllers. And we have controllers that we've developed that allow us to have linear complexity increase as we increase in degrees of freedom for high degree of freedom systems. And we also have various novel algorithms for control and manipulation. And as you can imagine, for many of these areas that I'm speaking about, we've really found that ROS can help a lot in our ability to perform in these areas. And let me give you a sample system that can show how we're utilizing this. And this is an example of a cell that we're striving to do palletization with. So the environment is that we have a mix of known and unknown but knowable elements. And this includes a set of tables with known location and dimension are the known elements. And the unknown but knowable are the locations of packages along with their dimensions, orientation, everything associated with those packages. These packages are randomly placed. They do have AR tags. And we also have a palette of known dimensions and location, which could also be unknown if we had an AR tag on the palette. In a database, we also have a mapping of AR tags to packages. So we basically understand the family code of what all these packages look like through an a priori database. The ecosystem that all of this is operating in is this environment that I've just described, plus a UR5 and a UR10 robot with some custom just vacuum grippers that we're using for manipulating these packages. The goal here is for the system to be able to accept a previously unknown order of a package mix. It will design a near optimal pallet load, and then it will actually create that pallet. And we'll see that in a moment. But the thing that we've used this system really to demonstrate is one of the emerging tasking standards that actually Craig spoke about briefly in the previous talk, which is the IEEE and Robotics P1872.1 robot tasking framework. And what you see here is the frame structure for this emerging standard. And we have basically a command frame, which is where all of these individual commands come through. Actions and sequences frames allow us to encode finite state machines and higher level plans. The results frame speaks to the kind of optimization constraints that we're looking when we're applying these commands and action sequences. And then we have specific constraints and resources that are available. And I'll show a little bit about how all of this flows through this system. And the way that we utilize this information and these structures is that we've built a comprehensive set of knowledge schemas. And these knowledge schemas represent all of the information that's in these various tasks. So we have things such as objects that are based off of a basic type. We have different types of goals that can be represented, and various types of predicates that we can use in determining if actions have been successful or if they're even enabled for execution. And what we've designed are generic types that can be specialized. And these generic types can be used across domains or specific types that we can have that are utilized in a single domain. So getting back to this, this example that I had spoken to, what you're seeing here is an RViz display of the actual robot system that's going to be operating, and then several different camera views of the robot. And this system is designed to work in 3 phases. Phase 1, we're going to see it actually construct a palette plan to build based on an order that it received. In phase 2, it's going to do knowledge discovery, where it learns where all of these randomly placed packages are. And then phase 3 is actually the construction phase. So what you can see is it receives its order and then creates a palette plan. And you can see the plan being displayed here in this RViz display. The robot will then move into the knowledge discovery phase, where it'll move to the end of the rail, and it will then go ahead and scan the rail. And as it's scanning the rail, you can see it recognizing and identifying these various packages. So these package locations are then being placed into the knowledge database, they're being instituted as instances of these pre-stored IDs. And it can then do an association as to which package has to be placed where in the system. What you can see now is that the two robots are working concurrently in order to actually build this, this pallet system. And what's nice is that this robot, for example, is not being treated as two separate systems of a rail and an arm, but it's actually operating as a true 7 degree of freedom system. And you can see this as that when it puts down a package, the rail will actually slide back to enable the package to be set down more rapidly and precisely. The coordination between these two arms is done through the use of predicates. And basically, we have a lockout predicate saying whether or not this, this coordination space is available. So we're using an escrow planning system that enables these robots to work independently and then have coordination points where they have to be coordinated for their motion. We're also doing some novel activities in the placement of these boxes in that you can see we actually are getting a very tight configuration. And we're doing that by using a force torque sensor to feel impacts of when the package is set onto the pallet. So we can scoot that package all the way into a very tight configuration. So what I want to talk about is how did we build this overall system? And this is actually a hierarchical system that takes advantage of a lot of features of the ROS infrastructure. And it starts at the lowest level with what we call actions, which in ROS tolerance are really action servers. And all of these action servers build off of our knowledge schemas and knowledge structures. And we're actually using ROS plan in order to interface with these actions. And what this allows us to do is we can actually have a low-level action that takes ASCII instance names as the arguments to that action, and then we reach into the database and ground these logical parameters with metric data. So this trajectory is a trajectory that's stored inside of our database, and it allows us to use this same single command to draw whatever trajectory we desire to draw, as long as that trajectory has been put into our database. And there you can see this is a novel controller that we have developed that uses a Cartesian path in X and Y and a force profile in Z. And what this allows us to do is to do things like drawing a logo without either pushing the tip of that pen into the marker or having a gap in the line. We also use this for things such as driving nuts and screws, such that we can maintain a constant pressure on the screw or the nut as we're driving forward. We also use this in terms of PDDL in that all of our actions have predicates that allow us to understand when these actions are valid to execute, and also what the expected effects are of all these actions. And by understanding the expected effects of the actions, we're actually able to do error detection by observing whether or not these expected effects happen. So now, if we move up a level in our hierarchy, we actually have the ability to encode finite state machines as what we call action sequences. And again, these obey a data schema that we have in place. And this allows us to have a single node that's able to read from this database and establish the ability to sequence out these finite state machine actions. So our PDDL planning system can then plan with these finite state machines as opposed to planning with low-level actions. And the benefit of this is that we're using open source AI planning tools such as PopF. And for that palette sequence that you saw there, that's several hundred commands that need to be executed. With PopF being a near optimal planning system, having that plan based on these lowest level activities really caused some strange plans. But as you can imagine, many of those activities are repeated every single time we interact with a package. So by creating a finite state machine with those activities, we can have the PDDL system have many, many fewer activities that it needs to sequence, and we get a much better plan out of this. Our ability here with these with these action sequences, we are able to do variable substitution. So an action sequence can accept variables and pass those down to our individual actions. We can also use constants if constants are required. So this is an example of using one of these action sequences. In this case, we are unscrewing a nut from a bolt shaft. And you can see that we have a series of 9 individual actions that are performed by this robot. And these are all performed by firing off the single action sequence of remove bolt and specifying again the name of the bolt. And the actual metric information associated with this bolt is stored inside of our knowledge base and is referenced by the low-level action servers in order to resolve the actual areas that the robot needs to move to. So here's an example of what the XML file might look like for one of these action sequences. And what you can see is that we have variables that come into the action sequence, and then we specify the individual actions with either variables from our tag here that will be substituted in, or we can have constants that are utilized. For instance, small positive Z offset is a system constant, and that would then be passed into the move as opposed to a variable. So as I had mentioned, we can then have a PDDL system that is able to use these action sequences as its lowest level of planning. And we can create really sophisticated behaviors by doing this. And what you see here is a PDDL environment where we have basically just said that we want this white part to be fixtured in this location. And the a priori environment understands that this part is fixtured currently in this location. And the knowledge base contains information about what kind of tooling is necessary for removing various parts, understands that this particular part has 2 potential fixture locations. All of this is built into our knowledge base. And what you can see here is this robot going through this sequence of 25 steps that it takes to move this part from one fixture to the other. But this includes activities such as tool changes, bolting, unbolting, everything of that nature. And these 25 high-level action sequences decompose into several hundred individual actions that the robot needs to perform. So I did want to just very briefly hit on one other novel control that we do have, and this is actually looking at very high degree of freedom system. In this case, we're looking at a 12 degree of freedom system. And again, we have finite state machines. In this case, you're going to see a 4-state machine that's sequenced through with a novel control technique that's being used for the different states. In the first, you're going to see in the next video that these 2 arms are going to move to an approximate position. And this is calling our 12 degree of freedom controller with a Cartesian constraint, where the 2 robot end effectors are trying to get within a constrained Cartesian position. We'll then move to a fixed separation, which is following a distance constraint for these 2 arms. We're then going to move into a state where we do optimized high degree of freedom trajectory following. And this is a combination of a Cartesian and distance constraint so that they can move this box from its current location onto this final resting location. And then stage 4 is we'll do a disengage, which again is a Cartesian constraint. So it's the same controller, but just using different constraints that are passed in as parameters. And if I play this video, you'll see these 2 arms doing these 4 different steps in the finite state machine in order to pick up this package and move this package to the location. And again, this entire system is being planned as a single 12 degree of freedom system to do this plan. So very briefly in summary, we're using ROS for all of these activities, and it really has allowed us to significantly reuse all of our services. It's allowed us the ability to utilize advanced open source algorithms and really have a robot agnostic implementation framework. The same algorithms right now are running on various UR robots throughout the family of URs, but we don't see any issue with porting them to entirely different robots. And really this implementation gives us an approach that provides really agility, flexibility, and ease of reuse and programming, and the ability to provide error detection and correction. So thank you. I think I'm out of time.